Okay, we're back for homework 5 part C. Homework 5 part C's question is derive the heat exchange rate for co-current and countercurrent heat exchangers and express in terms log mean temperature differences, and then explain the concept heat exchanger effectiveness and how it can be used in conjunction with NTU and minimization over Cmax ratio for heat sizing exchangers. So here I just have a heat exchanger. We have our temperature C in and temperature H in. And then we have our temperature C out, TH out, and then we have our DA in the middle. Sorry, it's kind of a lot of, I realized a lot of lines now that I'm seeing. So this is just kind of like an inner tube where hot water is going in, basically, or hot substance. So, and then over here on the right, we just have some terms that we will use along the way that will be useful. So we have Q equals M dot times CP times delta T, and we have DQ equals CH DTH, and we have DQ CCD TC. Okay, first what we're going to do is we're going to have to solve, we want to solve for our heat. So using formulas and what we have on our right, we know that Q is going to be equal to RU times our temperature H minus our temperature C, and then that's going to be times our area. So now we just need to derive this problem. So all we're really going to do is just put a D in front of this, and change it to just T, and then so when we do that, we'll get DQ is equal to U dt dA. And then we can solve for, well, we know that dt is going to be equal to dTH minus dTC. Okay, so now we can just simply rewrite what we have up here. And what we're going to want to do is solve for our d delta t. So when we solve for our d delta t, we're going to end up getting our negative dq minus over ch minus our dq over cc. And then when rewritten again, we're going to get d delta t is going to be equal to our negative dq multiplied by our ratio of our ch minus our cc. Cool. Okay. So what we're going to do now is just rewrite this again. So we're going to kind of sub these formulas in again. So we're going to get our d delta t is going to be equal to our negative u times our delta t dA 1 over ch minus 1 over cc. And then we can cancel units out. So when we do that, we're going to get 1 over delta t d delta t. Just trying to get rid of that delta t term. Well, not necessarily get rid of it, but kind of nullify it. 1 over ch minus 1 over cc dA. And then what we're going to want to do next is we're going to want to integrate. So let's integrate where we need to. So there, and these are constants, so here. And then when we integrate, we're going to get a natural log of delta t2 over delta t1 is equal to negative UA. Negative UA times the ratio again, this time negative. Cool. Now if we derive our starting expressions from up here, like up here, we know that we're going to get Q is equal to negative CH and then dTH, which is TH2 minus TH1. And then when we derive the other one, we're going to get Q is equal to CC times dTC, which is going to be TC1 minus TC2. And when we rewrite that into these that we just solved for into when we rewrite those into what we already solved, we are going, or up here, we're going to get natural log of TH2 minus TH1 over TC1 minus TC2 minus UA times the quantity 1 over, or not 1, sorry. Oops, go back. TH2 minus TH1 over Q, and then we're going to have minus TC1 minus TC2 over Q as well. And then we can rewrite this in terms of delta T, which is what we want. And then after that, we're going to have to solve for Q. So when we rewrite in terms, we're going to get ln delta T2 over delta T1 negative UA. And then we can pull 1 over Q out, so we're going to get 1 over Q. And then we're going to just have delta TH minus delta T, or delta TC. Or actually, we're actually going to not use T and C, we're going to use, or H and C, we're going to do 2 minus. Okay, and then when we solve for Q, we're going to get Q is equal to negative UA over, and then we'll have, in the numerator, we'll have T2 minus T1. I keep forgetting the delta. And then in the denominator, we'll have what is in the natural log. So there we go. That's what we get when we solve for Q. And that expression right there is the heat exchange rate for our heat exchanger drawn here in terms of LMTD. So now what we're going to do is we're going to explain the concept heat exchanger effectiveness and how it can be used in conjunction with NTU and Cmin over Cmax ratio for sizing heat exchangers. So there's a few things I'm going to write down and then I'll be back. Okay, I just wrote down for kind of relations. So we just have our heat exchanger effectiveness in this top left here. And epsilon here is equal to our actual heat transfer over our max heat transfer. And then we have heat max, which is equal to our Cmin multiplied by our delta T1, or Tn, sorry. And Cr is equal to our Cmin over our Cmax. So our Cr is kind of what we're looking at here in part 2. And how it can be used in conjunction with NTU. So our NTU here, as you can see, is like equal to UA times or over Cmin. So you can find NTU using Cmin, and you can also relate what we're looking at the question with NTU using these 4 equations. So if we know like the NTU value, say, of the heat exchanger, these equations can kind of be used in junction to find unknown values like when temperature, or required area when temperature isn't known, and other useful things like that. So that is kind of how heat exchanger effectiveness and how it can be used like in conjunction with NTU and our ratio, so to like find different values that may not be known or are unique for the specific heat transfer unit.